Classical Physics, Chapter 1, Newton's Law. Now, before Newton, the Galileo did all kind of experiment. Now, the existence of gravity is known before Newton already. Okay, for example, the legend said that Galileo dropped the object from the Tower of Pisa, and they proved that there is no difference between heavy material and the light material to fall. The speed is same. Well, this is unrealistic experiment because this gravity, 56 meters tower, it takes only 3 seconds, and the time they don't have a good watch. There's no way they can measure anything in that kind of fast speed. Okay, but one thing Galileo and other scientists talk about existence of gravity. Okay, even Aristotle, 1,000 years ago, he expressed the gravity the way saying that things like to go down to the ground, and that's his expression of the gravity. Okay, so the gravity was there, and Galileo was the establish all the speed, acceleration, and the force, those concepts, and he did many experiments. Okay, and what it is he used very clever method of measuring speed of the rolling ball on the board, inclined ball, because this way F is effectively get less. So it takes longer time to reach from top to the bottom. So it's easier to measure the time, and I don't have a detail of what kind of clock he used. Probably the famous one is swinging pendulum. Okay, so he used a swinging pendulum to see the clock ticking and the measures time it's arrived. If you incline more, then it takes longer time, so it's easier to measure. So he knew the gravity, and he knew the force can be reduced by inclined ball, and the speed, concept of speed and acceleration. Okay, those are all there before Newton's. Okay, now he also knew about the friction. He tried the piece of metal sliding and put the oil to reduce the friction, and he came up to the ball. Ball has the least friction. So if you experiment the metal, oily surface, and ball is gradually reduced friction, the result become approaching to the finite result, which is the ideal case, the no friction case. Okay, just extend the graph, then you can tell. So he was very clever doing that. So he could measure using inclined ball, and the ball which has very minimum friction. Did all kind of experiment, speed, acceleration, and force, and speed times time is gonna give a distance. Okay, and he also come up with this average speed. Okay, when there is a constant acceleration, the speed increase from 0 to gt. So average is this. So the distance is going to be average speed and the time t. So it's going to be gt square. Okay, so Galileo even calculate the case for the constant acceleration. But beyond that, you need a math tool, which is calculus. And another important thing is Galileo also imply there is a things called inertia. And what's happened is after the ball rolls down to the bottom of the inclined board, it keeps going. Why it doesn't stop right there? There's no more acceleration. So he knows without acceleration, the object keep moving, and that's inertia. Okay? So the concept of inertia is there already. And what he is great about is that he established a scientific method. What is scientific method? Okay, you do experiment, you make a hypothesis and do the experiment and confirm the hypothesis. If experiment shows the violation of hypothesis, that hypothesis is wrong, experiment determine whether your hypothesis is correct or not. This is scientific method, and even now every scientist stick to this method. He was the first one to establish. In that sense, he was great scientist. Okay, so Newton admit that according to Newton's word. He said, I could achieve my work by standing on the giant shoulder to see far out there in the science. Okay, now all the basic preparations laid out by Galileo, and also there is one more. There are a lot of work done by Kepler and Copernicus for the planet movement. There are a bunch of data taken by them. Okay, so one time Newton was teaching in the university and had a plague, and he went back home and has to stay a couple of weeks. So he decided to integrate all the data, Galileo's and Kepler and Copernicus, planet data and Galileo's work. He stayed in his room for 2 weeks and tried to figure out and connect them all together. Okay, so here comes the famous story, Newton's apple. Apple fall, he found out gravity, but that is totally wrong. Gravity was known already. So what he did, he expanded the concept of gravity to universal level. Planet movement and falling apple, they are same gravity. And that's Newton's discovery. It's not that Newton discovered gravity by falling apple. Falling apple, the Galileo and the scientists prior to Newton already knows there is a gravity. But he connected the dot from here to planet motion. And that's what Newton did. That was a great work. So he established the universal gravity. Gravity work on planet as well as apple. And that's the Newton's work. Okay? But Newton wrote, during that 2 weeks, he established first law, second law, and the third law to derive all the motion of the mass. And additional book described the gravity, and this is dedicated for planet movement. Okay, so Newton actually come up with the gravity is going to be proportional to the inverse of distance square. Okay, this distance square is the key, because all the planet data taken by Galileo, Kepler, Copernicus, it's the planet are always going around the sun along the ellipsis orbit, and ellipsis orbit imply 1 over r square force, and Newton came up with this. But that time he didn't know gravity constant or what sun's weight, or planet weight, the mass. So this was just one constant. So its constant is like A, and this will explain why planet go around ellipses. But checking this ellipsis size and speed, then he can separate parameter because G is common to all, M is common to the planet, and M is individual to the planet. He separate each parameter, then come up with estimated planet mass, sun's mass, and the gravity constant. Okay, so that's how he worked it out. The key is that the force acting on planet is proportional to the inverse of distance square, and that was a key. And Newton was great in that sense. He looked at the data and ellipsis orbit is what kind of force is going to cause ellipsis orbit, and that's the equation. And he applied to everything like the apple whatever, and it's come up to be pretty much that gravity force is acting on apple everything, so universal gravity. Okay, now he didn't clarify what the mass is. So mass, Newton's words is earth is everything, so weight on the earth was the mass, but actually mass and weight is different. We have to make this distinction. When you say Newton's law, F equals ma, this is a mass, not the weight. Okay, the weight change because the mg is a weight on the earth, and 1/6 g mg is going to be the weight on the moon. So we have to make a distinction between the weight is the force, pulling force by gravity, but mass is intrinsic. So what is the mass then? Is if you look at the periodic table, all the atom has a mass, and everything in this world is made of atoms. So you add up that mass, and that's the mass. Okay, and that wasn't clear, the Newton. Okay, and inertia. Why inertia? The first law, inertia, was the first law. Okay, the Newton, using calculus, if F is 0, then ma equals 0. So A is 0, which is dv dt. Then V equals C. So what is this C? Okay, there's no way to determine this C, but inertia law helped. Inertia law is before any F is applied, it was C. So it's the inertia speed. And in order to change inertia speed to something else, you need a force. So by solving this calculus equation, it can be any speed, but physically it has to be the inertia speed before the force is applied. Okay, so it's so-called initial speed before you calculate the trajectory. The inertia speed is what it is. That's why the Newton's law, the first one is establish inertia speed, and the second law is F equals ma. Now, action reaction. Let's talk about force. Newton's force. Newton has any idea what the force is, but he just generally say force. The force you know, and I know, generally force. But there are only 4 fundamental force in this world right now. The force, the one Newton identifies, the gravity, and electromagnetic force, and nuclear force, weak force, and strong force. There's no other force. The friction is come down to this. The molecule bonding come down to electromagnetic force. Okay, so there's only 4 different force here, and he didn't know, but he just say force, and that's happened to be very universal, and this equation works for any kind of force so far. Not really for nuclear force, but electromagnetic force and gravities, this works very well. Okay, so the mass and force was generically defined in Newton's world, right? And speed, acceleration, those are already defined by Galileo. Okay, so action reaction. How do you justify action reaction? Action is actually you give a force, then you get force back, right? And so this is a universal law, and it works for almost any force, electromagnetic force, gravity, and stuff. Okay, so this things often ignored in those Hollywood movie, right? The one guy, using superpower lift entire stadium, right? But in reality, before stadium goes up, he's gonna be plunging to the ground, because action reaction from stadium is gonna push him down deep inside the ground. So there's no way he can lift up the stadium, and that's Hollywood. Okay, ignoring physics law as usual. It's fun stuff, but this action reaction seems to be universally works. Okay, that's why Newton's saw a great success. It became a base of the science, and not only science, engineering. It's like mechanical engineering and designing building, bridge, all kinds of things works very well. Newton's law, and even electromagnetic field is when it comes to force, Newton's law works very well. And also thermal engineering, we can do molecule level thermodynamics that's used Newton's kinetic energy, so it works very well. Okay, so but there are kind of force, we name the force centripetal force. What is that force? Is that a real force? Okay, let's talk about this a little bit. When you have a gravity force for the satellite, and the satellite going around the Earth, okay, how comes astronaut feel he's floating? No force. It has a gravity force, but he doesn't feel it. Why? Because we explained that saying centripetal force is acting on it and it's balanced out, so there's no net force. He's floating. Okay, in reality it's not true. He is falling by the gravity. Okay, but he has a inertia going this way, but gravity changed this direction. So gravity force is used only for changing the direction. So F equals ma. This force is a vector, and this vector affecting only the direction only, and this is constant. Okay, so what happened is, without gravity you are flying off the tangent, but the gravity change your direction. So in a sense, actually you are falling by gravity, but it's falling, the this speed is too fast. So instead of falling to the earth, it's falling around the earth. Okay, and all the gravity force is used for changing the direction, and the speed is same as a result. Okay, and that's why centripetal force is a fake force, just to explain why astronaut feel he's floating, and it's a perceived force. He perceived as a force acting against the gravity. Actually, that's the inertia. Okay, so that's the preparation for actually getting into the Newton's mechanics. The first law, the second law, third law, and gravity. They are the basic law that Newton established, and we use them and dig into more details. Okay, I hope you enjoyed these videos, and if you like, please subscribe and move on to the next section of chapter 1.